the next aspect of motion we're going to look at is projectile motion. So one of the things firstly is, well, what is a projectile? How is it different from other types of motion we looked at? But also, what are some similarities and how can we actually apply what we already know from analysing motion to this type of motion? So the first thing is, well, what is projectile motion? So projectile motion is an object that's in the air and the only thing that is acting on it is gravity, nothing else. So no propellers, no jets, nothing. So if we were to analyse the forces acting on this, if we just had an object in free fall, then the only force acting on it would be weight, so due to gravity. We're going to ignore air resistance to start with. So the first thing just to note is we're going to ignore air resistance. But even if I'm projecting these at a bit of an angle, still the only thing acting is weight down. Doesn't matter where it is, that's the only thing. You'll also notice too that these types of objects, when we project them at a bit of an angle, follow a parabolic path. And there's a reason for that as well, which will become clearer later on. So before we go any further, when we look at projectiles, one of the things we're going to do is consider the velocity at any given point. And if, for example, here we've got someone jumping off a diving platform, when they initially project themselves off here, they jump forward, but as soon as they leave that platform, they start to fall. And you can see here again that they're following this parabolic path, and at any given point on the path, the velocity is given by the tangent to the curve. So what we can do with that velocity at any given point is it can be broken into two components, just like any other vector we've analysed. So what we can do is resolve it into two components, and one of those is horizontal and one is vertical. And why is that, you ask? Well, we're going to analyse what happens to these two components because they're not the same. If I just was to consider an object being dropped straight down, then the only thing acting on it would be acceleration due to gravity, and everything you've known about vertical motion under gravity would apply. What happens to the horizontal component? Well, if we don't have any air resistance, that component of the velocity is not going to change throughout the flight. And I'll show you what I mean by looking at an applet. I've got an applet here, and what I'm going to do is I'm just going to reset it so that the angle of projection is horizontal. So I'm just going to change that, it should be 0, and reset. And if I start it, so what we've got here is I've just projected something. This is started from about 5 meters up, and what we're going to do is consider or break it into two components. So if I just reset that and play, so here when I project this one horizontally, it lands about 5 meters. That's the horizontal distance, or the range is where it lands, and that takes about 1 second. So what I'm going to do now is I'm going to show you the velocity vector. If we reset that, so what happens now, and I'm just going to slow it down a little bit, is initially there's only a horizontal component of the motion, because, so we're going to break it into two parts. So this horizontal is 5 and the vertical is 0. Just as if you drop something vertically, the initial speed would be 0. So if we start this, just want to watch what happens to the two components of our velocity. And just notice here, I want you to watch this horizontal value. Notice this value here, it hasn't changed. And what's happening to the vertical value? you should be able to see here that the vertical value is getting bigger. The horizontal is unchanged. And of course, as you get closer and closer to the ground, as you would expect, that vertical component is getting larger and larger. So what we can do here is analyse the two components, and what we can see here is that, if I reset, is that the horizontal does not change, but the vertical is getting bigger. So the sum of those two components will always equal our velocity. If I was to make the initial speed greater, so just increase it, what would we expect to happen? Well, presumably it should go further or have a bigger range, as you can see here, because I'm making that horizontal velocity greater. Therefore that component contributing to the velocity is greater, and we get a bigger range then of about 8 meters. So to start off with, we're just going to consider only horizontal projection with no air resistance. So just again, what we've got here is that the acceleration due to gravity is 10 in the downward direction. No other forces act on our projectile. Now, what would happen if I were to project an object horizontally and drop one at the same time? This is I suppose, a type of thought experiment. So what would happen if I dropped something and projected it at the same mass object, everything the same, but we projected one and dropped the other? What would happen? Let's have a look. Alright, bit fast, let's do it again. So here what we've got is an object being projected and another being dropped more or less straight down, and let's see what happens. I'll just step through a bit more slowly, and you can see the objects, the next frame, reach the ground at the same time. Because both are subject to acceleration due to gravity, which is 10 straight down, there is nothing else acting on them. So even though one has a horizontal component, it doesn't change throughout the flight. It's still going to fall at the same rate, even if it does have a horizontal component. But you're saying, well, gee, that's not very fast. What if I project it really, really fast? What would happen then? We can use the analogy of famous thought experiment is when, what if you fired a bullet from a gun and dropped the bullet at the same time? Same again, they should get to the ground at the same time. And as long as the ground is level, obviously, obviously the Earth's surface is curved, but for our purposes, they should strike at the same time. Again, the acceleration in the horizontal direction is 0 because the velocity is unchanged, and the acceleration due to gravity is 9.8 or 10, which is down. So we should get the same result no matter what. What's going on here? Well, what you're basically seeing here is that as the object is dropped, or the egg, it has a forward component of its velocity which remains unchanged, and it will keep pace with the bird as it moves forward. So the minute the egg is released, it's subject to acceleration due to gravity, and it's still got the horizontal component, so it matches the speed at which the bird is moving as well. Horizontal component remains constant, but the vertical is subject to acceleration due to gravity. So just to sum up, just as we've seen before, our velocity component in the vertical direction is increasing, our horizontal stays the same. So what that means is we can use our equations of motion for constant acceleration to analyse the vertical component. To sum up, so these are our components. You might find this handy to write down. So in the vertical direction, the acceleration is -10, whereas in the horizontal, the acceleration is always 0. There's a constant velocity. This means that in the horizontal direction, you can just use distance on time because that's not going to change. And for horizontal projection, the initial component of the vertical velocity is 0. To find the vertical height so that it drops down, you can use your equations of motion like ut plus half at squared. That's if the time is known. Otherwise, we can apply some of our other equations if we don't know time. To find the horizontal range, then we'd use our velocity times time. Now, the key thing here, of course, to keep in mind is that the t value is the linking factor between these two components. So for both, the time is the same. So t is your linking variable. It's the same for both components. So let's look at applying this to some problems. If we take a horizontal projection, I do believe Top Gear actually did do this at some point. In this case, I'm actually given the initial horizontal speed as 12, and it tells us that the time of flight was 3 seconds. So I've got that linking factor. So once again, I would write down what I know, which is 3 seconds. And what I often do is write down, well, what do I know in terms of horizontal and vertical components. So for both of them, we know that t is 3 seconds. On the vertical, I know that the horizontal initial speed is 0, and I know that vertical, I know also that the horizontal velocity is 12. Now that will remain the same throughout the flight. That is not going to change. So to find the height of the cliff, we need to consider the vertical components. So in this case, I know the initial speed, I've got the time. I also know, of course, that my acceleration is -10. I could ignore the negative here because it is falling all in the same direction as the height. It just gets a bit more complicated when we have projection at an angle. So here, using my equation of motion, x equals ut plus half at squared, that would end up being 0 plus, I'm going to ignore the negative sign just because it's all in the downward direction, half times 10 times 3 squared. So I'm left with 5 times 9, which is 45 metres. Because it's just asked for the height, it's 45 metres. If it wanted the displacement, of course that would be -45. So how would I find the horizontal range? Well, we know that the horizontal range is given by the velocity times the time, because there's no acceleration in that direction. So we're left with 12 times 3, which is 36 metres. Now, as our projectile falls, this tangent, or the velocity, is the vector, gets bigger and bigger. And when it hits the ground there, you're going to have your velocity vector, and we can break it into two parts. So the last question is, well, how would I find the actual velocity it hits the ground at? So to find the velocity that it hits the ground at, I need to know what both components are. So if you consider that when it hits the ground, it's a velocity broken up into two components, and I'm going to have my horizontal, which we already know because that's 12, it hasn't changed, but I need to find my final velocity when it hits the ground, and we know that occurs at 3 seconds. So which equation? I've got u, I've got acceleration, I've got t, but I need to find a v. So which equation could we use? if you've got v equals u plus at, 0, I'm going to ignore the negative sign just because it's all in the same direction again, and I've got that my final velocity will be 30. So how we find v is using Pythagoras. So my final velocity will be the square root of 30 squared plus 12 squared, and when we work that out I get 32.3 or just 32 if I use significant figures meters per second. Now of course if it wants an angle that it makes with the ground, we would also need to use some trig there to find the angle, and you could use tan for example in this case. I'm not going to work that out right now, but if you wanted to find the angle that it makes with the ground, it would be tan of 30 on 12. So that would give us 68 degrees. So just to recap there, when we're looking at our projectile motion, firstly with horizontal projection, we need to break the motion into two components. That's the easiest way to do it. There are other approaches which could take into account energy considerations, but just to start with, this is a common way we would approach it. So break it into two components and take it from there by using your equations of motion.